Alright, thanks for the introduction. Actually, I'm a little bit nervous because we just passed the demo. I don't have a demo in the slides. So anyway, hello everyone. Today I'll talk about using a single networking device for object recognition and navigation. This is a joint work with my colleague Yunshen, my advisors, and Heather. Autonomous devices get lots of attention today. In the near future, we'll see many exciting applications like delivery drones, medical assistants, and companion robots. To be fully autonomous, these devices need to move around with mobile imaging. Imaging is not just the localization. It also tells us the object's shape and even material. This helps the device go through an unknown environment and find the correct target. For example, suppose a robot gets in a room to get a shipping box. Imaging can help the device move around without collisions, but more importantly, it can help the device identify and pick up the right item, the box, of the specific size and the cardboard material. To achieve this, the imaging system must be accurate and robust in different environments, like in the darkness or in the rain. Also, it should be low cost and portable. To meet these requirements, previous work uses 60 GHz networking radius. Well, they have some clear advantages, but the solution needs two separated mobile devices. Well, for some scenarios, two devices may not always work, right? It would be much more practical if we only need one device. So in this work, we use one device for imaging. This could open up many exciting applications where only one device is available. But what does it mean to use one device? It means that the transmitter and the receiver have to be close together. They're now co-located. This makes the system much harder than before because previous algorithm doesn't work anymore. Because co-locating the radios will change the reflection conditions. Let me show you. Previously, the transmitter would stay static as an anchor point. So the receiver can move meters away from the transmitter and capture many reflections. Here, the receiver will get the reflections from the entire object surface. But when we use one device, things are changed. Now the transmitter and receiver are just tens of centimeters apart with a fixed distance. They move together and they both rotate the beams to get the reflection signals. And because of this, we only get the reflections from a small surface area. This brings new challenges to the system. An obvious challenge is that we don't have a fixed anchor point anymore. Since now the transmitter moves with the receiver. So the previous algorithm, which relies on a fixed transmitter, doesn't work anymore. Also, because the 60 GHz radios are close together, the amount of reflections we get become very limited. The reason is that the 60 GHz signal will reflect off the surface like a mirror. So our signals can only illuminate a small surface area as opposed to the entire surface. This means we need a device to move around and detect these small areas and then recover the surface. One way to do this is to find the precise location of these small areas and then simply put them together. But unfortunately, we can't get their accurate locations because the device will move and doesn't move in a perfect way. That means that in a traditional algorithm, we will locate the center point of each illuminated area using the phase of the signal along the device movement. By the way, for those of you who are not familiar with the term phase, it's just the property of the wireless signal. But you know, when the device moves and tracks its movement, we always get some errors. These are tracking errors. These errors will corrupt the 60 GHz signal phase, even if it's just millimeters. And this means we don't have the accurate information of these points anymore. So the only reliable source we have is just the signal strength. But obviously, on a single device, the signal strength itself can't magically give us more information. But because we're using the 60 gigahertz signals, we also have their beam directions because they will align the beams to capture the reflections. So we can use the beam directions to compensate this missing information. So our paper has two major contributions. One is to allow the device to move around objects safely. We did this with only the 60 gigahertz networking radius. Also, we proposed the new imaging approach using the received signal strength. We don't use phase of the signal for the system robustness. Instead, we use the 60 gigahertz beam directions. In this talk, I'll focus on the second part. So next, let me talk about how exactly we can do imaging with just the 60 gigahertz beam directionality and the signal strength. The key of our solution is to model the surface in a way so we don't have to pinpoint or locate each individual point on this surface. What we did is to consider the surface as a sequence of small flat segments. Each segment is a tiny flat surface block that connects every pair of the center points that you saw. What's great about this is that segments have orientations, and they are naturally connected together. What this means is that if we can detect these segments with orientations, we can connect them together to recover the surface shape, and we don't need to locate each individual segment anymore. So at high level by physics, we can approximate these segments by projecting the device trajectory after we get their orientation information. But of course, this approximation isn't enough. The surface, location, and the size are correct yet. So we need to relocate and resize the estimated shape. Our trick here is to estimate the whole surface location or the surface center from the directional signals we get, rather than individually pinpoint each location of the segments. So given the time limit, I'll focus on orientation and the surface shape. But don't worry, we didn't do the rest of this by magic. We did this by physics and geometry. And you can refer to our paper for more details. So how can we derive the orientation with just the signal strength and beam directions? We did this by finding the specular reflections. The specular reflection is the strongest mirror reflection from the surface. To capture this, the transmitter receiver will rotate their beam to record signal strength, like the beam alignment process. They can find the beam directions that lead to the maximal received signal strength. These are the specular reflection directions. By geometry, we can use them to estimate the orientation of each surface segment. In particular, we use them to derive the normal line of each segment, which is perpendicular to them. So with the orientation information, we can now estimate the surface shape. To do so, our key insight is that the surface segment and the device movement are correlated, because both of them can be quantified by every two consecutive measurements. For example, suppose we get two specular reflections during the device movement. We now have a tiny device moving distance between the two measurement locations. It can be a centimeter or even smaller based on how fast we take the measurement. And recall that the surface segment is also defined by the two center points of the reflections, so they are strongly tied together. Because of this, we can approximate the surface segment by projecting the tiny device movement, like what we've shown right here. Remember that the surface segments are naturally connected, so we also make sure to connect the estimated segments during the projection. This will ensure the estimated surface shape to have the same geometric properties as the actual surface. Then by geometry, we can resize and shift it to the correct position. So that's how we did imaging. The entire system also considers navigation that guides the device to move and sensing that detects the existence of an object. We only use the 60 gigahertz signals to do it. 60 gigahertz networking radius to do this. And here's an illustration. Suppose a robot just enters the room and there's an object. We first need to scan the environment and we would know where to move safely. So we did this based on the fact that nearby object must reflect the signal. So we can compute a safety region based on the reflection measurement. And from these reflections, we also sense if there's an object. So the device will move inside the safety region, collect the reflection signals, and output the imaging result. We repeat this process until the robot recognizes the target or finish scanning the room. So we validated our system and built a prototype with two 60 gigabit networking radios. The radios follow the wireless communication standard and we can perform real-time beam steering. As shown in the figure, each radio has a 16 by 8 antenna array, which gives us a narrow beam. The arrays connect to the baseband on the development board and we mount them on the body car. The car tracks how far it moves by wheel rotation, and it moves with arrows as large as 10 centimeters. As is shown here, even though this is just a prototype, our device is very compact. By the way, we did not put other sensors on this robot device. So we evaluated our system in both indoor and outdoor environments. In particular, we experimented in rooms of different sizes, from large classroom to narrow corridor. Overall, we tested 11 common household objects. They vary in size, shape, and even material. So our results show that the system can achieve centimeter-level accuracy. For the object location size, the detection error is less than 8 centimeters. We can also narrow down the materials to 3 candidates. All these require very low computation complexity. The analysis can finish in a second for measurements per meter of the device movement. So here is an indoor imaging example of 2 different boxes. And from the figure, we see that our result is accurate and it's comparable to the existing camera-based solution. We also did some preliminary tests in the outdoor parking lot, and here is the result of the car backdrop. So the navigation of the system is also accurate and robust. And here is a snapshot of the narrow corridor, which is just 2.5 meter wide. The device is surrounded by multiple objects. Although the estimation is conservative, the safety region can accurately capture the impact of different objects. Even the object, the 5 centimeter wide pillar on the wall. So with this accurate estimation, the device can navigate around without hitting things. The right figure shows the navigation path for the device to find the metal cylinder. So in conclusion, we designed and implemented a single device imaging and navigation system. We did this with only the 60 gigahertz networking radius, using the signal strength and the beam directions. Our next step is to handle the 3D imaging scenario and study multi-path influences. Also, since we're using the networking radius, we'll further study the balance between the communication and imaging functionalities. That concludes my talk.